Hello and welcome back to Probability Theory, the video course where we talk a lot about random stuff and how we can use it in statistics. Indeed, in today's part 34, we will start talking about the inferential statistics. This one is also often called inductive statistics, and we will start with it by defining statistical models. However, as always, before we go into this important definition, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. Moreover, as you might already know, you can download additional material for the videos by using the link in the description. And with that, I would say let's immediately recall the idea of inferential statistics as we have discussed it in the last video. So usually what we just have is a statistical sample, so a finite collection of points from a whole population. And exactly from that we want to extract information such that we can say something about the whole population. For example, it would be nice to say from which random distribution our sample comes. Or if you want to ask it differently, what is the underlying random variable x? This means in this case we have x from omega into r to the power d. And there d is the size of one point in the whole sample. And here you immediately see this is a really hard problem because we can have a lot of different probability distributions that can produce the same sample output here. Therefore, in explicit examples, you would definitely make some further assumptions about which distributions fit the most. But still, in the end, you have infinitely many possible distributions you would put into a set. So we have abstract probability measures we can call P with index theta. And then this index goes through a whole index set we denote by capital theta. And with this notation, the overall goal of statistics is to find the most fitting parameter theta from this index set. And for that reason, we also call capital theta the corresponding parameter space. And there you already see, choosing a good parameter space is already part of doing good statistics. In general, this parameter space should not be too big, such that you can do actually something mathematically, and it should not be too small, such that you don't lose any information. And then a statistical method will tell you which probability distributions fit the data. And how much they fit we also would measure with some probability again, and usually we call this probability a likelihood. But more about this later, let's first look at an example to see what we can choose here. There, for whatever reason, we already know that we have a normal distribution as the underlying probability distribution. And we can make it even simpler by assuming that the variance of the normal distributions is always equal to 1. But on the other hand, the mean is unknown, which means we can choose it as our parameter. Hence, in this example, the mean of a normal distribution will be denoted by theta. So maybe if you want to get some real-world application into this example, you can just think of measuring something. Let's say you want to measure a temperature by using a thermometer. And this thermometer cannot be completely precise, such that you already know that you have the variance given as 1. And moreover, you can also already estimate in which range your measurement will lie, so you can also restrict your parameter space theta. So you don't have to get all real numbers in, maybe from -5 to +5 is enough. This means now in a mathematical way again, all the probability measures are fixed as p theta. And it's given by the normal distribution with the mean theta and the variance 1. Hence the set of possible distributions is quite concrete in this case, because we just have the normal distributions where the mean is the parameter. And now in the next step we can discuss what is the most suitable parameter theta if we have a sample given. Obviously there is no unique answer for this question, so we will build a whole framework to answer it. So you know, the only thing we have here is a sample with n entries. So it's a sample of size n, and maybe to keep it simple, let's say that the dimension d here is equal to 1. This means every entry in the sample xj is a real number. But maybe the given problem already tells us that we don't have to consider the whole real number line, so we can restrict the possible values of the samples. So it's just a simplification to make the whole space smaller, and we call the sample space X with index n. So it's a subset of Rn, and every sample has to come from this space. And that's why we call it the sample space, but please note this is in the statistical sense, so it's different from the notion we had in probability theory. Actually, this notation overlap is not a problem at all, because from context you always know which sample space we actually mean. So in this case, this double xn is called sample space, simply because every statistical sample lies in the space. On the other hand, in probability theory, we have the notation capital X with index, which denotes a random variable. And this one is usually defined on an abstract sample space omega. So you see, we have a lot of similar symbols and names, but from context it should always be clear what we actually mean. Here, for example, capital X1 is a real valued random variable. And actually, to interpret our sample from before, we could say that we have n random variables here. So we have capital X1, capital X2, and so on until capital Xn. And then our interpretation is, if we put in a lowercase omega, we get out our sample. So xj of omega is equal to lowercase xj. So again, we just interpret the given sample as the outcome of n random variables. However, since each point in our sample should represent the same measurement process, also each random variable here should not be so different from the other ones. In fact, these random variables should just be different realizations of the same underlying random variable for our statistics. Therefore, the family of random variables should be independent and identically distributed. And there you already know, the usual abbreviation for that is just IID. So overall, this is just a modeling procedure that helps us to find the underlying distribution. Then it does not matter that we choose n random variables, because they have the same distribution anyway. So with all that in mind, we can finally define our important definition to model statistics. In short, this is just what we call a statistical model. So first, as before, we just fix the sample space Xn, which could also be the whole Rn. Moreover, we also take the possible distributions for our problem and call them p theta. However, as you now know, p theta is a probability measure on R, but we need it on Rn. Therefore, we have to make the step to the product measure, which we denote by p theta n. So this is not so complicated, it's just the n-fold product measure. And this simply allows us now to measure subsets in our sample space Xn. And for that reason, we will consider the Borel sigma algebra on Xn. And then instead of just one probability measure p theta n, we consider the whole collection of product measures. Which simply means that we consider a whole family of probability spaces. And exactly such a general family is what we call a statistical model. So we definitely use what we have learned in probability theory, but the whole setup here is put in such a way that it is ready for applications. So in particular, for a given statistical model, we want to find the best fitting theta. So you can keep already in mind, for a given sample, we want to estimate a fitting theta. And there we will distinguish two essential procedures. The one is a point estimator and the other one an interval estimator. However, there I would say, this is definitely a topic for the next video. So I really hope I meet you there again and have a nice day. Bye bye.